Far away, almost to the North Pole, is an international science research station on an island chain called Svalbard. Here, Dominique Seles, a physical geography major from Worcester State in Holden, Massachusetts, is studying currents coming from underneath the Kronebreen glacier in beautiful Svalbard, Norway. What? Currents from under glaciers? Aren't glaciers made of ice? Yes, but here's a little fun fact. Those glaciers are wet underneath, and that is why they slide. And there could be plenty of liquid water flowing under and through glaciers that come out of the glacier and empty into the ocean. Dominique wants to know the speed of those currents.
So Dominique, why do you want to know the speeds of the currents from the subglacial streams?
Well, if we know what the speeds are, we can get a much better understanding of melt rates and the whole glacial complex in general. And so by knowing the speeds of, especially of that surface plume that's coming out, so when that subglacial stream enters the fjord, it enters that margin, it shoots up the face of the glacier, and then it comes out along the surface of the water. And that current, by getting the speed of what that current is right at the surface, we can get a much better idea of what discharge rates are, sedimentation, and those sorts of processes in general.
That's really interesting.
To measure the speed of the current, Dominique uses a drogue. The drogue can be lowered to different depths, and the water pushes the panels on the drogue at the same speed as the current. There is a buoy on top so that Dominique can follow it. Dominique puts the drogue in the water and writes down the time and GPS coordinates of the drop. Later, Dominique returns and picks up the drogue and again writes down the time and the new GPS coordinates. Now it will just take a little bit of math to calculate the speed of the current. This is some of Dominique's raw data, and we're going to focus on the data she has here in line 113 for her drogue drop on August 6th, third drop of the day. She dropped it off at 2 p.m. and she picked it up at 3:17 p.m. and she's recorded the GPS coordinates for the drop-off and pickup locations. So I have transferred that information here. Those are the GPS coordinates and the time, and we know the formula for speed is distance divided by time. And I went ahead and figured the distance between those 2 points is 720 meters. And from 2 to 3:17 p.m. is 1 hour and 17 minutes, but that is actually 4,620 seconds. So plugging that into our formula for speed, distance divided by time, we get 720 meters divided by 4,620 seconds, and that is 0.16 meters per second. It'd be kind of fun to know what that is in miles per hour, just to give us a sense of how fast that is. So a conversion factor of 2.237 will work here because 1 meter per second is 2.237 miles per hour. So multiplying that times 0.16 meters per second gives us 0.36 miles per hour.
So the speed of the current turned out to be about 0.16 meters per second. Mm-hmm. So what are you going to do with that information?
Well, that was for the surface current, so that was being measured at about 2 meters depth using the drogue, and that was just one time. And so what we'll end up doing is averaging that speed of the current with either similar measurements in that area across different days, or comparing that to what measurements we got during different days, because it's a really dynamic system and it changes a lot from day to day. So one day the speed might be 0.16 meters per second, and then the next day it could be a lot slower. That plume might be inactive. So comparing that measurement to measurements we recorded on different days will definitely be one thing that I look at.
Now it's your turn. Dominique deployed her drogue many times, measuring at different depths and in different parts of the current. Let's practice calculating speed using the rest of her data.